A black hole that reflects light would turn the darkest engines of gravity into cosmic mirrors, rewriting the rules of thermodynamics and observational astronomy, reshaping how energy moves through space, and forcing us to rebuild our understanding of event horizons. If reflection replaced absorption, the accretion disks would blaze with redirected photons rather than swallowed radiation, and gravitational lensing would amplify and scatter beams like a gargantuan curved reflector, creating structured, possibly coherent light patterns. Reflective horizons would also erase the one-way boundary that defines black holes today, converting the event horizon into a photon-bouncing surface that stores angular momentum and phase information. And any surrounding plasma would become a high-efficiency light recycler that feeds back into jets with unprecedented brightness. A reflective black hole implies the event horizon is not an absorptive null surface, but a boundary with non-zero albedo and specular components, which would preserve information carried by electromagnetic waves instead of thermalizing it. This would immediately resolve the information paradox by allowing light to depart with encoded quantum states. But it would simultaneously violate the area law of black hole thermodynamics that ties entropy to horizon area. In effect, Hawking radiation would be replaced or joined by coherent reflected emission, defeating the notion that the horizon is a causal one-way membrane and nullifying conventional proofs in general relativity that mandate absorption when escape velocity exceeds the speed of light in vacuum. Reflection at the horizon would demand material-like properties, such as refractive index and conductivity, or an effective field layer. Yet standard solutions of the Einstein equations do not include such a surface and predict free-fall geodesics crossing the horizon without encountering resistance. To produce reflection, the metric or boundary conditions must change. Either quantum gravity induces a partially reflective firewall layer, or exotic matter stabilizes a thin shell that mimics the external space-time of a black hole while replacing the interior with a compact object. Astronomers already test similar ideas with gravastars and wormhole mimickers, where reflection is modeled as echoes in gravitational waves following a merger. If horizons reflect, gravitational wave detectors would consistently record late time, exponentially damped echo trains after ring downs, with amplitudes and delays tied to the compactness and reflectivity. Current data up to the year 2025 place upper bounds on such echoes, but do not confirm them. Electromagnetic observations would change radically. The Event Horizon Telescope's images would show brighter photon rings with interference fringes, because reflected trajectories would execute multiple passes near the photon orbit and superpose coherently. Polarization maps would carry the imprint of surface boundary conditions, letting observers infer reflectivity spectra across frequencies from radio waves to X-rays, rather than a purely absorptive silhouette.